it a little bit when we looked at the properties, laws, limit laws. I wanted to see if I can find it quickly. I just wanted to show it to you. I think it's before this. Don't get scared. It looks scary, but it's not. Okay, this is it. We're not going to use it right now. We will use it a little bit later in chapter 3. And I'm going to start with it then. If a function is continuous at b, then the function composition is continuous at f of b. That's all it says. So the limit of f of g of x, remember what I said even today at the beginning? Imagine this is the limit and this is the square root. So we put the square root outside and the limit next to the function. So this is exactly the first thing we looked at. I didn't recycle this yet. Because of continuity, this is possible because of continuity. So the limit of the function of g of x is f of the limit of g of x. So we use this. I didn't tell you. I only mentioned last time that this is possible on the continuity. So this is the swapping of the operators. And that's exactly what this is. Okay? So this first operator becomes the second operator. This is the second operator becomes the first operator. So here you see the limit is applied to g. Here the limit is applied to f. So if we reverse the order of f and the f operator and the limit operator, we reverse them. We put the limit inside and f outside, the swapping of the operators. This is possible only under continuity. Okay? So we are going to use this later on in a later chapter. You don't have to do anything with it right now. Just to remember that it exists and it's under continuity. Okay? If this condition is not fulfilled, we are not allowed to swap the operators. This becomes out, it goes out, and limit goes in. Okay, enough of that. If we don't have any other questions, I'd like to continue with something we started a long time ago. I think I'm ready to recycle that. Okay, it's in the recycling bin. So here we can add any addition, subtraction, multiplication, division, and function composition. This is function composition. Okay? So if I add two continuous functions, I get a new continuous function. If I subtract, I get a new continuous. So I subtract, if I multiply, divide, or function composition of continuous functions, the result is also continuous. That's all it says. And I showed you the limit, the property. Okay, so 2.6, limits at infinity. So a long time ago, which was probably three meetings ago, that seems already a long time ago, we had a little table. And on this side, we said infinite limits. And on this side, I wrote limits at infinity. Okay, what is all this? Infinite limits means limit as x approaches 0 from the right of 1 over x is... Can anyone picture the graph of 1 over x and tell us the answer? I'm really hoping that you immediately remember the graph of 1 over x. Forever. And can anyone give us the answer?
Infinity.
Very good. Which means immediately, if I determine the limit of a function and I get infinity, as a rational function, and I get infinity, then x equals 0 is a vertical asymptote. This is what we did in 2.2. Infinite limits means the result is infinity. And it deals with vertical asymptotes as well. Limits at infinity is a different story. Here I want limit as x approaches infinity from 1 over x. Limit when x goes to infinity. Here is when the trend, the result is infinity, but here is when x approaches infinity. Look at the graph and give me the answer, please.
0.
Yes. So when we find the limit at infinity and we get a number like this for a rational function, then we will write that y equals 0 is a horizontal asymptote. As you see, this is a horizontal asymptote. The trend is approaching 0. Here, when x approaches 0 from the right, the trend is the function goes to infinity. So here, for rational functions, I will find vertical asymptotes for rational functions. And here for rational functions, I will find horizontal asymptotes. For other functions, like for example, here's another example, the limit as x approaches infinity from e to the x. This is not a rational, and the result would be, I hope my students immediately remember, we graphed this today, a few minutes ago. This is the graph of e to the x. We don't like this function for the obvious reasons. Okay, what is the answer?
Infinity?
Yes. But here, this function doesn't have a vertical asymptote. This one does. This one does not, right? And also, it's a different story. We have the limit as x approaches infinity. I would like to refresh your memory on another very important function. So we know e to the x, we know 1 over x. Let's also graph natural log, very important. So we have it here. Here is natural log, is the inverse of this. So if you want to put it together, they have to be symmetric with respect to y equals x. And this is natural log x. Let me graph the other one when the base. So this is log base a of x, but the base is tiny. This, the base here, is greater than 1. It's e. That's why they're inverses of each other. For base greater than 1, log function is increasing. For base less than 1, any log function is decreasing on its domain. But I want to refresh your memory on arctangent. So f of x, I don't really like to write it like this. It's legitimate, it's correct. I prefer arctangent x, because a lot of students think that this is 1 over tangent. No, it is not. Not 1 over tangent. Arctangent is the inverse function of tangent. It has nothing to do with tangent to -1. That's the notation for the inverse function. So it could be confusing, but just remember they mean the same thing. Especially when I type, it's easier for me to write this than put the power. So I try to avoid this notation, but they mean the same thing. But it's not 1 over x, 1 over tangent x. Okay, so I'm going to graph both. Here I'm going to graph tangent. Tangent function, I hope you remember, please. If not, please remember it moving forward. So this is tangent x, and it has 2 vertical asymptotes. It does not exist at negative pi over 2, and it does not exist at pi over 2. Now, the inverse function will be similar to this. Of course, it has to be one-to-one and symmetric, but similar to this, meaning it will have horizontal asymptotes, the ones that you see here. So y equals pi over 2 and y equals negative pi over 2. And the graph has to be symmetric. Here's the graph. So this is the graph of arc tangent x. Please remember these two graphs. These are inverses of each other. So that's why this one looks like this, because they have to be symmetric with respect to y equals x. So here's the graph of arc tangent, which should be here, like this. But the units will not be the same. So that's why I didn't want to superimpose one on top of the other. So please remember, so now if you are asked, what is the limit of tangent x as x approaches pi over 2 from the left? What would you say?
Infinity.
Yes, which means x equals pi over 2 represents?
A vertical asymptote.
Excellent. For this one, what will you say? Limit as x approaches negative infinity of arc tangent x. What will you say?
Negative pi over 2.
Which means, excellent, y equals negative pi over 2, horizontal asymptote. Careful now, which we have not seen this in normal rational functions, right? At negative infinity only. Because at the other end is positive pi over 2. So when x approaches negative infinity, the function values get closer and closer, closer and closer to negative pi over 2, only at negative infinity. Because at positive infinity, it will approach closer and closer, closer and closer to pi over 2. This is never the behavior of a simple rational function. A simple rational function, as x approaches infinity, or x approaches negative infinity, it's the same horizontal asymptote. If it's a simple, pure rational function. But this is a totally different function. It's the inverse of tangent. It has a horizontal asymptote at negative pi over 2 to negative infinity, and a horizontal asymptote at pi over 2 when x approaches infinity. Two different horizontal asymptotes. Okay. The other thing I was going to mention is something we already did here. I started with that. So if we have the limit as x approaches infinity of 1 over x to any power, let's say power n, and n is definitely a number greater than 0. Because if it's negative, then it goes to the top. If this is negative 1, then this becomes x to the first power. If it's negative 2, it becomes x squared. What do you think this is? It's going to equal to. This is basically exactly the same, but I put a power here, which is positive. That's all that there is. What will the answer be?
Zero?
Very good. Awesome. Always 0. Perfect. I would like us to practice I'm going to share my screen right this moment. Let's look at 2.6 right here. And I would like us to look at, now do you think we should look here? Let's look here. For example, for this function, as x approaches negative infinity, what will the limit be? As x approaches negative infinity.
2.
Yes, very good. Follow the function, follow the function, follow the function, follow the function. Excellent. As x approaches 1 from the left.
Infinity.
Yes. As x approaches positive infinity.
Negative.
So we follow the function, follow the function. What is it?
-2.
-2, very good. It appears to be -2. You can say, well, I think that the function will do this. Yeah, you could, but it really says this. Okay, good. So I'd like to look at problems like these. So let's choose a problem. Anything you want to pick from 5, 6, 7, 8, 9, 10. Sketch the graph of an example of a function that satisfies all the given conditions. So please choose what
We do 7.
Which one?
7.
7 it is. Okay, perfect. So let me copy number 7.